So, good morning guys. Nandito po kami ng aking mga grupo para po mag-report sa inyo about STS or tinatawag nating Solar Thermal System or Conserved Raising Solar Power. So, let's go. So first, Solar Thermal System Operating Principle. Solar thermal power plants collects the energy from the sun with the use of mirrors. The collected energy is being reflected or redirected to a tube. This causes the fluid to achieve a high temperature. This fluid then transfers its heat to water, which becomes a superheated steam. This steam is then used to turn turbines in a power plant, and this mechanical energy is converted into electricity by a generator. So, ito yung paano gumagana yung solar thermal system. So, yung ginagawa nila, may fluid doon, tapos kailangan mag-achieve ng high temperature, then then yung fluid na to is to transfer yung heat to water, which become a superheated steam. So, ito na start para umikot yung turbine to generate power. So, yun yung ginagawa or paano yung operating principle ng solar thermal system. So, next. So, yung photovoltaic na kung naalaala nyo. So, yung ginagawa nyo parang energy source, tas energy conservation, tas energy inversion conditioning, tas energy distribution or storage para magamit yung energy na na-store. So, yun lang. So, next. So, nakikita natin kung paano nangyayari dito or paano ginagawa or nagge-generate ng energy. So, first, nakikita natin yung sunlight, nagre-reflect siya through mirror or para yung sunlight, nagpa-focus siya dun sa may glass para tamaan yung fluid. So, pag tinamaan yung fluid, magiging mag-iinit siya at magge-generate na ng energy para dumiretso sa generator and everything else to generate yun, electricity or energy. So, next is, ito yung mas complicated type or detailed explanation kung paano nangyayari dun sa loob. So, yung fluid out, yung reflection, nandyan na. Plus, yung parabolic shape, reflected trough, reflective coating of mirror. Nakikita natin, ito yung design kung paano itsura ng parabolic trough, tas yung paano umiikot siya, paano nagge-generate ng energy, and everything. So, next, dito nakikita natin yung basic diagram ng parabolic trough or kung paano nagge-generate siya ng energy from sa system or sa may mismong mga panel, tas diretso sa heat exchanger set, pupunta siya sa condenser, papunta sa cooling tower, or diretso sa steam turbine, papunta generator para magbigay ng electricity. So, next is parabolic trough collector, nakikita natin. Tapos yung hot salt cold tank. So, itong dalawa na to, yung pinagkaiba nila is yung pagkamukha muna. So, parehas silang may salt, molten salt. Kasi dito sila yung nagbibigay gabay sa energy. Or sila yung parang naglalagay ng kung saan patungo muna yung energy. Kasi magkahiwalay sila. So, yung hot salt, papunta siya sa turbine, diretso sa iba. Tas yung cold salt tank patungo sa pump, tas diretso na din para mag-meet at gumawa ng energy.
Steam turbine. A steam turbine is a machine that extracts thermal energy from pressurized steam and uses it to the mechanical work on rotating output shaft. Its modern manifestation was invented by Charles Person in 1884. Fabrication of a modern steam turbine involves advanced metalwork to form high-grade steel alloy into precision parts, using technologies that first became available in the 20th century. Continued advances in durability and efficiency of steam turbines remain central to the energy economics of the 21st century. The steam turbine is form of heat engine that derives much of improvement in thermodynamic efficiency from the use of multiple stages in the expansion of steam which result in a closer approach to the ideal reversible expansion process. Because the turbine generates rotary motion, it can be coupled to a generator to harness its motion into electricity, such as turbogenerator are the core of thermal power station, which can be fueled by fossil fuel, nuclear fuel, geothermal, or solar energy. About 85% of all electricity generation in the United States in the year of 2014 was used by steam turbines. Parabolic tube is a set of concave mirrors that concentrate solar rays on the receiver tube that is located in the focus. This tube can track the sun around one axis, typically oriented north-south, to ensure the highest possible efficiency. The fluid flows through this tube and absorbs heat from the concentrated solar energy. Similar to a parabolic tube is a linear Fresnel system. Its collectors resemble parabolic tube but use long flat Fresnel mirrors. This is technology. This is much cheaper to install but has lower efficiency. Example are limited to a few plants. Synthetic oil or molten salt mixture is usually used to circulate through the heat exchanger tubes and absorb heat concentrated by the mirrors. This fluid usually gets heated up to 400 to 600 degrees Celsius. The tubes then deliver these oils to the process. Operating principles of potential transformer. The potential transformer working principle is based on Faraday's law of electromagnetic induction. Through two primary windings and one secondary windings make up a potential transformer. The high voltage line that needs to be stepped down is connected in parallel to primary windings. The secondary winding is linked to a measuring device such as a voltmeter or wattmeter to measure the voltage or power in the circuits. A magnetic field is produced around the primary winding when a high AC voltage is applied to it. This magnetic field induces a voltage in the secondary winding. A large number of turns of a conducting wire are built into the secondary winding, which aid in stepping down the voltage to a lower level. HTF or heat transfer fluids. A heat transfer fluid's operating range is the temperature range between the pumpability point and the recommended maximum bulk fluid operating temperature. The pumpability point is roughly defined as the temperature where a fluid's viscosity reaches 2000 centiliters. At this point, the fluid becomes too viscous for centrifugal pumps to maintain sufficient fluids flow. Although heat transfer fluids technically can be used at temperatures close to their pumpability points, many fluids, especially petroleum-based fluids, lose much of their heat transfer ability and efficiency when used close to their pumpability points. A fluid's ability to withstand thermal cracking, thermal degradation, is the primary factor in setting its maximum bulk fluid operating temperature. This temperature is the maximum temperature the fluid manufacturer recommends. The fluids can be used and still maintain an acceptable rate of degradation over time. Typically, a good fit between a heat transfer fluid and an application happens when the required fluid temperature of the process falls right in the middle of the operating range of the heat transfer fluid. Discussion on either side of The operating temperature allows for good overall heat transfer efficiency and minimal fluid degradation. One quick rule: there is no reason to consider fluids that have maximum bulk fluid operating temperature below the bulk heat transfer fluid temperature required by your process. Cross those fluid off your list right away. And even if a fluid is used at a continuous temperature close to at least recommended maximum fluid operating limit, there is a point to take into consideration. The thermal degradation rate is not a linear function versus temperature. As the bulk fluid temperature reaches exceed the fluid maximum recommended temperature, the degradation rate soars asymptotically even when used within 15 to 20 degree Fahrenheit of the recommended maximum temperature. The degradation rate of most heat transfer fluid is significantly higher than when application requires a temperature within 30 to 50 Fahrenheit of fluid's maximum temperature. The cost associated with increased fluid makeup rates, the downtime required for heat transfer, fluid related maintenance, and lost heat transfer efficiency due to degradation by product have to be strongly considered when choosing between a lower cost fluid that will be bumping up against its maximum recommended use temperature and more expensive fluid that will fit nicely right in the middle of its operating range. Question: why use HTF instead of direct system in which water in solar thermal or CSP? In the view of improving the efficiency of solar thermal power plants, much research is going on the field of heat transmitting fluid, liquid metal, fissure gas, ceramic, and nanofluids are the prospective material to be used as HTF. Sodium has high working temperature and very low solidification temperature. I intended to know the reason of not using its not HTF other and its vigorous reaction with water.
Okay. Types of HF. The heat transfer fluid used in CHP technologies are air, water, molten salts, glycol-based, glycerol-based, and synthetic oils. But air and water are not used anymore. Why? Because in the meticulous design of CHP systems, the deliberate exclusion of common substances like water and air as HDF is not arbitrary but rather rooted in the agencies of the solar energy capture process. Water characterized by a relatively lower heat capacity in air susceptible in undesired phase. Changes at high temperature fall short when subjected to rigorous CSP operation. In contrast, HTFs emerge as a class of substances carefully engineered to withstand an extreme condition with the solar power plants. The resistance to decomposition and evaporation at elevated temperatures ensure not only the reliability but seems the continuity of the energy transfer process. Okay, next. Okay, these following characteristics are considered what type of HDF is to be used in a solar thermal system. First, operating temperature. Second, life cycle and heat transfer capability and heat storage aspect and overall safety, and most importantly, the cost. Note, the uses of molten salt in parabolic through system can heat transfer the fluid up to 550 degrees Celsius. Has better performance in synthetic oil that only 400 degrees Celsius 400 degrees less. Okay, now. And also, a central efficiency heat transfer fluid is their unparalleled thermal sustainability. The characteristic is not merely a technical nuisance. It's a leap into the sustainable functionality of the entire CSP system. The ability to resist decomposition and degradation at high temperatures become a cornerstone ensuring the longevity and reliability of the energy transfer medium. As a CSP system operate in diverse environmental conditions, many HTFs are formulated with a low freezing point. This seemingly subtle characteristic plays a crucial role in preventing the fluid from solidifying, especially in colder climates. The avoidance of solidification safeguards the fluidity of the HCF, preventing the disruption and ensuring the system's continuous operation. HCFs are not merely conduits of heat. They are meticulously crafted mediums and designed in an optimal heat transfer. The efficiency with these fluids absorption of solar energy with congruity minimizing less energy loss become a hallmark of their contribution to the overall efficiencies of CSP system. The unseen battles with CSP systems involve the constant integration of HTF with the intricate network of pipes and heat exchangers. Corrosion resistance emerges as critical characteristics, acting like a shield against the insidious effects of degradation. By ensuring the integrity of the system components, HCFs contribute significantly to overall durability and resilience of the CSP technology. Okay. And the adaptability of the HDF is not confined to a narrow thermal spectrum. That these fluids exhibits a remarkable versatility operating to a broad temperature range, ranging from negative 30 degrees up to 400 degrees Celsius. HDFs demonstrate a flexibility required to accommodate the diverse thermal demands of the various CSP applications. This expansive temperature range positions them as a versatile agents in pursuit of sustainable energy solutions. As a CSP technology evolved, the quest for higher efficiency, prosper exploration for innovative applications enter molten heat transfer fluids that a testament of the dynamic nature of CSP systems. By utilizing the HCF's advanced power plants can achieve even higher temperatures, pushing the boundaries of electricity generation. This approach expands the horizons of what CSP technology can achieve, unlocking new frontiers in sustainable energy production. Okay, now, in mirrors, receivers, and heat transfer fluids, the seamlessly transfer of solar energy in CSP system, the deliberate exclusion of water and air, coupled with the nuisance characteristics of HTFs, underscores their indispensable role in renewable energy production. As ESP technology advances, the continuous of refinement and exploration of heat transfer fluid promise to unlock a new sustainable utilization of solar power. In embracing HTFs, we embark the journey toward a greener and more sustainable future, when the sun's energy becomes not just potential source of reliable and efficient contributor in our global energy needs.
Okay, solar tower. Type pa rin siya ng SDS. This is setup includes an array of large number computer-controlled sun tracking mirrors known as heliostat. Sunlight can be concentrated as much as 1,500 times its normal intensity. This mirror moves in dual axis, which means it moves north to south and west to east, and are located at the ground level, which collects energy from the sun then reflects it towards a receiver which contain HTF or heat transfer fluid. HTF is located at the top of the tower. The HTF is being heated at around 600 degrees Celsius. And just like in the parabolic through, this HTF through pipes, it goes to a set of heat exchangers. Then it transfers heat to water, thereby generating high pressure, superheated steam, which is being used to turn a steam turbine. Okay, solar power tower. In the parabolic through, tinatrack niya yung araw through one axis only. And it moves from east to west. Samantalang ang SPT ay dual axis, kaya kaya niyang mag-move north to south and east to west. Ang pag-collect niya naman ng heat from the sun ay it will reflect that directly to the thermal receiver sa taas ng tower. Sa taas ng tower, mayroon pa ding HTF na maiinitan at pupunta ulit sa heat exchanger. And all the types of SDS is the same pagdating sa operating principle, but difference is the manner of way of collecting sunlight. So, the schematic diagram of power tower is the sun go to the heliostat or the mirrors na i-collect niya naman papunta sa central tower receiver. Then, heat transfer fluid mapupunta sa heat exchanger. Pero may mapupunta din sa hot salt tank to preserve the heat, the hot water, to steam turbine to produce electricity, to function the generator. Then next is to the condenser to turn the gas into water again. Then next is the pump, is to pump the water into heat exchanger set to HTF, pero meron pa ding mapupunta sa cold salt tank. Then, yun, cycle lang.
Okay. Linear Fresnel reflector, general description. This design of this type is a combination of parabolic through and a solar tower. This uses flat mirrors instead of parabolic mirrors used in parabolic throughs. These flat mirrors moves in one axis only, unlike the solar tower and the parabolic through dish, which move in two. It adapts the working towards working as of a solar tower, where the mirrors on the ground collects the light from the sun and reflects it toward the fixed receiver located above. The classic LFT has only one linear receiver on a single linear tower. To increase optical and ground use efficiency, the improved design called compact linear Fresnel reflector use multi-force receivers for each set of mirrors, so the adjacent mirror have different mirror inclinations in order to the different receivers. Okay. Solar power with a linear Fresnel reflector, a technology that ingeniously transforms sunlight into a usable energy. The inner workings of LFR, from its distinctive diagram and solar field configuration to the creation of thermal energy, is convertible into electricity in the continuous improvement through the design revisions. Okay, next. Okay, this are the advantages and disadvantages. The disadvantage of LFR is it uses a flat mirror, which is much cheaper than the curved mirrors that used in parabolic throws. And one of the big disadvantages of this design is the shading adjacent mirror, which can be encountered only during the utilization of the ground space, which increases the cost. Very high temperature are not also produced as compared to the parabolic through of the solar tower. Therefore, their efficiency is less. And now we see that there's a simple diagram of how LFR works. Like the sunlight is reflected by the reflector and then redirected to the absorbent tube that produce the heat. Okay, next. Here's now the much more detailed diagram of how LFR works. Okay, a reflective surface. Okay, a reflective surface working together to maximize and capture the sunlight. This expansive area is adorned with mirrors, each playing a crucial role in redirecting sunlight towards in the receiver. A diligent team ensuring that every beam of sunlight is harnessed and making it a key player in efficiency of entire LFR system. As sunlight coverages the entire receiver, it generates a thermal energy. This heat becomes valuable resources, setting the stage of conversion of solar power into a form of we can use. This section delves into the science behind the production of thermal energy within the LFR, underlining its potential as a sustainable and clean energy source. Okay. This is a roadmap guiding us through the intricacies of capturing and converting sunlight. The diagram showcases us a linear array of flat mirrors which strategically positioned to track the sun's movement. These mirrors work collectively to direct sunlight onto the central receiver, where sunlight takes the lead into the production of renewable energy. Okay, next. This newer version of an upgraded version of our LFR, the compact linear Fresnel reflector. In the technological process, LFR is not just static but undergoes a continuous refinement through the design and revision. Ongoing research and development effort focus on enhancing its efficiency, durability, and economically viability. This segment explores the intricate nature of LFR, illustrating how each revision propels the solar technology forward, making it increasingly effective and accessible in the renewable energy landscape. Okay, next. Okay, parabolic dish. This consists of a set of flat mirrors combined from the large parabolic dishes that is attached to a motor sensor which tracks movements of the sun in a dual axis. The collected energy from the sun is being concentrated to the PCU located from the focal point of the dish. The PCU consists of mainly a thermal receiver and Stirling engine. The transfer its heat to the Stirling engine causes it to reciprocate. The reciprocating movement causes the rotation of an electrical generator. These dishes can concentrate sunlight much better than parabolic through and fluid run through them can reach a temperature upwards of 750 degrees Celsius. But there's a limitation of the size of the small quantity of the fluid. Parabolic dish collector suitable for small scale generation up to few kilowatts. Okay, now the Stirling engine. The Stirling engine is a sealed cylinder from one part of hot and cold. The working gas inside the Stirling engine which often air, helium, and hydrogen. When the gas is on hot side, it expands and pushes through the pistons. When it moves back to the cold side, it contracts. At the heart of the parabolic dish lies a Stirling engine, a compact powerhouse from that transforms solar thermal energy into mechanical power, operating on the cyclic compression and expansion of a working fluid. The Stirling engine plays a pivotal role in the parabolic dish, ability to turn sunlight into electricity with an unparalleled precision. This section takes a deep dive into mechanics of Stirling engine, illustrates how it is harnessed the sun's warmth and converts it into a movement that ultimately generates electricity. Okay, next. Now here are the largest solar thermal power stations. We have the largest Arzate solar power station found in Morocco that was made way back from 2018. It uses a parabolic through and a solar tower combination. With the area of 2,500 hectares with a capacity of 510, and we also have Ibanpa Solar Power Facility, Mojave Solar Project, Solana Generating Station, Genesis Solar Energy that was made on USA and made when on the span of 2013 to 14 with an area of from 714 hectares to 1,920 hectares. Now we also have a Solaben solar power station that was found in Spain that can produce 200 megawatts that uses parabolic through. It was made on 2012 that only uses a space of 301 hectares. Next. Now, here's another one, the Mohammed bin Rashid Al Maktoum Solar Park Space 4. That a combination of parabolic throw and a solar tower that can produce 600 and 100 megawatt capacity. This was still ongoing. That started from 2002. That was found in Dubai and UAE. That's all.